Welcome to the first chapter of this course, Modular Monoliths: An Introduction. Let me give you a brief overview of what we are going to cover in this lesson. We are going to talk about monoliths and microservices and do a high-level comparison of these two architectural styles. We are also going to talk about architectural drivers, which are requirements that help us decide what is the correct architectural choice to make in a given context. We are also going to discuss the benefits of microservices and monolith style systems, and then we are going to introduce modular monoliths as a combination taking the best of both worlds from these two architectural styles. Let's start with a simple question, and that is, what is software architecture? A simple definition could be that software architecture are the design decisions related to the overall system structure and behavior. This relates to the components that are parts of your systems, such as any applications, databases, and other external services that you might be integrating with, and typically software architecture decisions have a very big impact on the qualities of the software system that you are developing. I also wanted to mention a funny definition of software architecture that I heard in the past, and that is that software architecture is the decisions that are expensive to change. And the only reason that I find this funny is that it turns out to be very true once you start working with software architecture extensively. The two most popular architectural styles are monoliths and microservices. And while I don't think that we should compare them in an either-or fashion, there are still some valuable insights that we can gain from doing a high-level comparison of these two architectural styles. So let's go ahead and do that. Let's start with the monolith architecture, and the first thing I want to do is to set a clear definition for what I consider to be a monolith. And that is that a monolith system should have exactly one deployment unit, no more, no less. So typically a monolith system is going to contain just one application, one executable that is deployed as a single deployment unit. Now, this doesn't mean that we can horizontally scale a monolith and have multiple instances. That is perfectly fine, but we still only have one deployment unit. Another important aspect in monolith systems is how the communication between the different components works. And in this case, the communication is very simple using in-memory method calls. This is fast and efficient, and it's a significant advantage when it comes to performance. We also have to talk about scalability because monoliths are often said to be less scalable than a microservices system, and I don't think that this is necessarily true, but let me explain what I mean. You can both vertically and horizontally scale a monolith, so you can add more resources to your monolith system, such as a bigger CPU or more memory, and you can also scale out the monolith to have multiple instances. But the problem with monolith scalability is that it is less resource efficient compared to a microservice. And this is because that when you scale a monolith system, you are scaling the entire system. While in reality, there could be a part of the monolith system or even a single component that really requires the increased scalability, and if that component was a single microservice, it would be trivial to scale just that part of the system. But inside of a monolith, you don't have the ability to do this granular scalability that you can do with microservices. And one more thing I want to mention, which is a big advantage of monolith systems, is immediate consistency. Monolith systems typically have just one database. This means that you can interact with your database in a transactional fashion, which guarantees you immediate consistency. On the other end of the spectrum, we have microservices. What I mean when I say microservices system is a system that contains many deployment units. These deployment units are logically and physically isolated services that come together to form the microservices system. Because we are now in a distributed system, the communication between the services has to use network calls. This comes with many other challenges, such as serializing the data and sending it over the network, integrating with various communication protocols, authenticating between the services in a distributed systems, which is why communication inside of a monolith system is much simpler. When it comes to scalability, microservices come out as the clear winner because you can both vertically and horizontally scale your services, and you can do this in a very resource efficient way. And another challenge that you will have to solve in a microservices system is eventual consistency, because you are now working with many different services and each of these services has its own database. Here is a visual representation of the concepts that I was just talking about, and this one refers to the number of deployment units. Inside of a monolith systems, you might have many logically different components inside of a single application, but they are all deployed in a single deployment unit, which could be a Docker container. In a microservices system, you can still have the same logical components that are now deployed into different deployment units. In this example, that could be multiple Docker containers. One more thing that I want to highlight is how the differences in the number of deployment units impact the communication between the components in your system. So inside of a monolith system, your components can communicate using method calls in memory. And inside of a monolith systems, only the components that are physically deployed together can talk using method calls. The components that are deployed in different deployment units have to talk using network calls, which means they have to serialize data and send it over the network, authenticate with the service that they are trying to call, and let's not even start a discussion about the reliability of network calls. Another quality that you get when you are working with monolith systems is that you will typically have just one database. Databases offer transactional guarantees, which means that you can get immediate consistency when you are talking with your database system. In a microservices system, each deployment unit or each microservice will have its own database. And while a single microservice with its own database can be immediately consistent, it's very often required to synchronize the data between different microservices. And this process is typically eventually consistent unless you want to do distributed transactions or two-phase commit, which introduces a whole nother set of problems. So which one of these architectural styles is better? Well, we can't responsibly say that monoliths, or modular monoliths for that matter, are better than microservices or the other way around. As software architects, we have to make our decision in a given context. And in order to understand what the correct decision is in a given context, we can use architectural drivers. Architectural drivers are a set of requirements, and there are four major groups of architectural drivers. These are technical constraints, business constraints, functional requirements, and quality attributes. Technical constraints are an architectural driver that include design decisions that are usually made by the development team, and these are decisions that are hard to reverse in the later stages of a project. Examples of technical constraints include programming languages, the use of a specific library or framework, or having to develop an application for a specific operating system or runtime. Business constraints are architectural drivers that impact the business side of your system. Examples of this include timing or any hard deadlines that you might have when architecting your system, and another business constraint could be a fixed budget to complete this project. Functional requirements describe what your system should do and how it should do it. Examples of this include requirements like the customer should get an email confirmation when their order is confirmed, or all customers should get a refund when an event, like a concert, is cancelled. One more architectural driver is quality attributes. They are also collectively known as ILITs. Examples of quality attributes include scalability, availability, testability, modularity, and maintainability. And while quality attributes represent the non-functional requirements of your system, they are still critically important for your system to function correctly. So when we are deciding which software architecture to use, we should keep in mind these architectural drivers and use them as a guide to help us make the correct choice in a given context. As a software architect, you also have to think about how the architectural decisions that you make today will impact the business many years into the future. It's important to understand that there is no such thing as free lunch, and you should use microservices when you need to. Microservices are there to buy you options such as scalability, independent deployability, zero downtime deployments, isolation of data, and so on. However, you have to realize that all of this comes at a price. If you are building any kind of distributed system, you need to be familiar with the fallacies of distributed computing. And the first one is that the network is reliable. Hint, it's not. Here's another fallacy. Latency is zero, and in reality, nothing could be further from the truth. Bandwidth is infinite is another common fallacy. The network is secure. Network topology never changes. There is always just one administrator for the entire distributed system consisting of dozens, hundreds, or thousands of different components. Transport cost is zero. or in other words, it costs you nothing to send data from one service to the other. Or does it? And the last fallacy of distributed computing is that the network is homogeneous. I hope you don't mind my humor while recounting the fallacies of distributed computing, but the thing is that so many developers try to build distributed systems without even considering how different the constraints that they are working with are compared to a monolith system. If there is one thing that you should get from the fallacy